Welcome to a video demo on thin film interference using a soap solution and a light source. Before we begin, 3 objectives are at hand. First, visually observe the various construction of wavelengths, an explanation of the physics involving interference through a medium in air. In this case, the thin film is the soap solution. And third objective, why do we see the bands of different colors? Okay, so here you could visually see that there are various colors of various thicknesses. That's due to the varying thickness of the film itself, due to gravity pulling the film down, thicker at the bottom, thinner at the top. This phenomenon up here, the black band, is due to the film being too thin and there being complete destructive interference. If you were to do the math, around 300 nanometers would be the first instance where all the colors through white light hit their maxima. So when you have a black band of complete deconstructive interference, right below it you'll have a white band as all the colors come to a max, and then the varying colors underneath. Oh, that's a good one. You have yellow, reds, purple, green, blue, all represented from the wavelengths of the visible, that are visible, 400 being blue, up to 700 being the reds, and everything in between. Okay, so here is the physics behind what we observed. Air has an index of refraction of 1.00. Water, in this case our soap solution, is approximately 1.33. Now a phase change due to the index of refraction goes by this rule of thumb. High of low, no change. Low to high, pi, or in other words, a half wavelength. The Fresnel equation gives us how much of the light is reflected at the interface between the air and the soap. And in this case, it's approximately 2%. And some simple math, just 1 minus 2% is 98% transmittance goes through the first interface. Here we have a diagram as to what we're seeing. On the left I have a light source, and it is the rays are normal to where the bubble solution, the soap solution is, so that all the rays coming across are perpendicular to the thin film. This in regards to like mathematics and conceptually speaking makes things easier. Okay, so I'm dealing with white light, which is well, I got the various colors here coming across. And here's what happens. You got your first interface of the film, right? And the ray comes in, and some of it, 2% of it, is going to reflect out. And some of it's going to continue through, 98%, And when it hits that second interface between the soap and air, again on the backside, is again going to reflect some more. Okay, so now we have the thin film sandwiched between air, and we go from low to high, and then high to low. Okay, so all the rays coming out are out of phase. Okay, so since all these rays being refracted are out of phase due to the rule of thumb here, the reason why we see colors, and we only see colors that are constructively interfered, is due to the path difference. L, the thickness of the film, and in this case, gravity changes the thickness, gradually gets thicker at the bottom and thinner at the top. Okay, so to figure this out, we first need like the interior wavelength, which will be the wavelength divided by the index of refraction. Then we could use that, and if this was a symmetric, consistent film and wasn't continually changing, we would be able to use m as an order number, which is an integer number, multiplied by the interior wavelength that we found, and divided by 2, which would give us 1L, one pathway across. However, the path difference is going to be twice that, since we have to go through the film and back through it again. Okay, so now that we know the physics behind this, where you see red, blue, green, it means there is constructive interference there, and all the colors in between as well. For your like oranges and purples, it means there's multiple colors superimposing themselves upon each other. And that is the thin film demonstration.